Here we have two graphs of f and g, and we're asked to find where is f times g continuous. You'll notice this graph has a couple breaks in it, namely at x equals -3 and at x equals +2. So it's around those 2 points we need to evaluate these expressions to determine if this graph is continuous. Let's start with the limit as x approaches -3. As we approach -3 from the left on f, we get 0, and as we approach -3 from the left on g, we get 4. 4 times 0 is 0, so the limit from the left is 0. Let's also check the limit from the right, because they need to match in order for it to be equal. As we approach -3 from the left, or from the right this time, on f, we get 0. As we approach -3 from the right on g, we get 2, and 2 times 0 is 0. So this left-hand and right-hand limit at -3 are 0. So we have the value of 0 there. What's the actual value of the function at -3? Well, the value of f at -3 is 0. The value of g at -3 is 2, and 0 times 2 is 0. So these values match, and therefore it is continuous at -3. But now the question is, what about at x equals 2? Will we get a match here and here? What's the limit from the left at x equals 2? As we approach 2 from the left, we get -4. As we approach g from the left, or as we approach 2 from the left on g, we get +2. 2 times -4 gives me -8. We're not quite out of the woods yet, though. We have to make sure that matches on the right-hand side as well. As we approach 2 from the right on g, on f, we get -2. As we approach +2 from the right on g, we get 4. 4 times -2 is also -8, so that checks out. What is the actual value of the function of f times g at x equals 2? The value of f is -4, the value of g is +2 2 times -4 is -8, and these values also agree. So it seems this function is continuous everywhere else. So we're continuous on the parts where there's no breaks, and we have to be continuous at the breaks, insofar as the limit value and the function value match at 3, or -3, and they match at +2. And so with that in mind, the function is continuous on its entire domain.